Welcome to JK Math Academy. In this session, we will be talking about algebra for beginners. This is the first lesson we are going to look into. And in this lesson, we will be doing some fundamentals of what is required to get into algebra. We will start with prime numbers, and as per this list, we will go one by one. And most often than not, I'll be concentrating on examples rather than verbose English. So finally, we will be ending this session with what is called as like terms, which is one of the fundamental concepts of algebra, which we will be learning. Thank you. The first concept we are going to learn is what are called as prime numbers actually. A prime number is something which can be factored by 1 in itself, that's all. That means, for example, if we take the number 17, we can say 1 times 17 is 17 or 17 times 1 is 17. There is no other numbers that can be multiplied to get 17 without a remainder. Those kind of numbers are what are called as prime numbers. They have only two factors. These are some interesting facts you can read for yourself. Basically, 2 is the only even prime number. Just for some quizzes and all, that will be helpful for you. And most important is 1 is not a prime number, because any prime number has to have two factors, 1 and itself, like 19 and 1, 3 and 1. So that is what it means by saying we have to have the exact, that is what is a prime number. So let us, in this section we will be learning about factoring, and this is also called as prime factorization, because we factor out the primes or the prime numbers from the number to get these factors. And the reason why we factor these things is to get something called as LCM, which we'll be seeing in the next section. So take for example 48 here, and see how we are factoring this. We are doing 2 times 24 is 48. Then because this is a prime, we don't do anything with this next. Then 24 is again factored out with 2 and 12. And 2 12s are 24. That's what we are trying to do here. Again the same thing. 2 we ignore, we go to 12. 2 times 6 is 12. And then we do 2 times 3 is 6. So basically these are the prime factors, 2, 2, 2, 2 and 3. When you multiply these together, you will be getting what is the actual number 48. So this is what we call as factoring. Why we need to do this, we will see in a future section of the same lesson. And what we have tried to do is bring the prime numbers. That's what I have explained here. 2, 2, 2, 2 and 3, which are in red color here, are the prime factors of 48. There is no one way to find the factors actually. You can do in many different ways. For example, in the last section of the same number 48, we use 2 times 24 and 2 times 12 and so on. Here I am trying to show that the same thing could be accomplished in many different ways. Here I am trying to do 4 and 12. Now because 4 is not a prime number, we will have to go to the next step of finding the primes of 4 actually. So that's what we are doing here. Now 2 and 2 are prime, so we have nothing else to do here. Go back to 12. So we can do 2 times 6, we can do 4 times 3, we can do 3 times 4, we can do anything, 1 times 12, whatever we want to do we can do, but 3 times 4 is what I am doing here, and 3 is a prime again, which is divisible only by 3 and 1. That is why we leave it alone here, and then we further factor 4, which is 2 times 2. The same concept we apply again. We take out all the prime numbers 2, 2, 3, 2, 2, and we would get the 48. So whichever way you take out, ultimately whatever prime numbers you get will total out or will be the product. When you multiply them, the product will be exactly the same number, 48. So I'm trying to explain here that it could be done in multiple different ways. I could have started off with 6 times 8 is 48 and then try to factor out differently. So that is what we are trying to explain here. Let us see two more examples here. I am trying to bring out some kind of a concept here so that you can understand. Both are odd numbers here, 39 and 79. Both have stopped at one level in the hierarchy, and there is where we got the factors. For example, the factors of 39 are 3 and 13. These are the only two numbers that can divide 39 without a remainder. That's why they are factors there. And both 3 and 13 are primes. There's no further division we can do there. We cannot find any further products except 1 times 3 is 3 and 3 times 1 is 1, and 1 times 13 is 13 and 13 times 1 is 13. Here it is the same case. 1 times 79. 79 is divisible only by 1 and 79. But the difference between 79 and 39 is 79 is a prime number because it can be divided only by itself and 1. Whereas this is not the case in the case of 39. 39 is divisible by 3 and 13 actually. So 39 is not a prime number, whereas 79 is a prime number. That is what I am trying to demonstrate here. Now let us do some exercise which I want you to do. Try to use the inverted tree process that we used there, but that is not essential. You can just draw some pencil lines and do that actually. No need to do any figures and all that stuff. So try to find the factorization or the factors of 80 and 60. Two simple examples for you to figure out the factors. This is a very critical step. So please do this. I have given the answers there, but try not to see the answers first and then try to factor out and get your answers. There are four things that I am mentioning in this slide. One is what are variables, what are constants, what are grouping symbols, and what is equality inequality symbols. These are all very simple to understand, but when we use them, we have to be very careful, specifically in real problems, and how to use them. For example, constant. 2 in this is a constant actually. It cannot be changed. A constant is a number whose values always stay the same. So 2 will never change actually. 2 will never become 5 or 1, but x could be anything here. So that is not a constant. That is a variable. And variables are, it could be a, b, x, y, any alphabet actually. It could be any alphabet, but by custom or by convention, people normally you will see that people are using x and y actually. So we have to be clear, but it could be anything. It could be y, it could be f. You yourself will be seeing as we go forward. From y it will go from x to y, then from y it will go to f actually, and we will see those are the stages we will come across, and be ready for that actually. That's what I'm trying to say. And another important factor I want to bring up here is multiplication in algebra is denoted with a dot. That is very critical, because the reason why they do that is, if you say x times x and use x as the multiplication symbol, it will look like x, x, x. So that is why a dot is used. And also when we come to decimals, we will see how a dot and a decimal differs. If I had to say 5.6 or 5 times 6, how do I specify that? So we will see all those things as we go forward. And then there are grouping. Grouping is basically parenthesis. We will see in this section itself, maybe we will see, or if not, we will see at some point in time. And then there are equality symbols I mentioned here. For example, a not equal to b, a less than b, a less than or equal to b, a greater than b, a greater than or equal to b. We will be dealing with all of these in the future. Here I am trying to mention these because these are all critical things that we need to keep in mind before delving into algebra. There we should not be figuring out what is a less than b symbol. What is the symbol actually? The left arrow or the right arrow, left arrow and underscore. All these we should be very clear here itself, and then we'll go. Moving on to another important concept, we are going to see what are expressions and equations in this section. First, I'll explain you what is a term. Anything standing individually like this, 5, 6, b, a, all of these are called terms actually. 2y here, I'll come back to this later, but 2y as a term here. So these are all called as terms actually. When an arithmetic symbol comes in between, it becomes an expression. Any symbol that comes between two terms is called an expression. We'll be dealing with terms more in this section, this session itself. So these are called expressions. What is the difference between an expression and an equation? See, for example, this is an expression. If this is an expression, this is an expression. And this is itself as an expression. 13 is an expression because we said this is a term. This is a term, but still it is an expression only. In an equation, the difference between an expression and an equation is that two expressions are differentiated or separated with a equal to symbol. If you see this, every one of these in this is having an equal to symbol. 6 plus 7 is an expression. 13 is also an expression. Also, it is a term actually. So 6 plus 7 equal to 13 becomes an equation. 7 times 7 equal to 49 is also an equation because it says equal to. And this is an expression. 7 times, see times here we have used a dot. This is an expression y plus 9. 2y minus 3 is an expression. 2y minus 3 is an expression. So there is an equal to symbol in between. So y plus 9 equal to 2 minus 3 is an equation. We need to understand this because a lot of things we will be doing in algebra with expressions and equations. We should never confuse between these two. The way to differentiate this is to see an equal to symbol. If it is not, it is just an expression. If there is an equal to symbol, it's an equation. And both of these are important and we'll be dealing with them in multiple places actually. And what is the difference between an expression and an equation? Beyond that, an expression is what we can simplify. We'll see how to. In this case, 5 plus 6 is 11. That is what is the simplification. When you say simplify, basically it becomes 11. Here, unless you know the value of x, you will not be able to simplify further. 7 times 8 is 56. You will be able to simplify this. 9 times 3 is 3. That is how you simplify this. A divided by b, you can't simplify any further. That is the most simplified form of this expression because you don't know the values of a and b. Equations, what we call as evaluate. So when you say evaluate, 6 plus 7 equal to 13. So if you add these two, it becomes 13. So it becomes 13 equal to 13. Basically, that is what is evaluation here. Here, if you know the value of x, or you have to find out the value of x, if x minus 7 equal to 15. We will be doing all this actually. Even this is an equation. So when we see expressions, we can simplify them. When we see equations, we can evaluate them. So these are the two things you have to remember. They'll say simplify. They'll say evaluate. This is how you will get your problems. So at that time, I don't want you to be thinking about what am I supposed to do with this. So you should know that if it is an equation, you have to evaluate it. And if it is this expression, you have to simplify it. This is a very critical thing you need to recall and remember. Before moving further, let us look at another important concept which is very important to do even the next steps actually. So what we call as order of operations. How do we do when we have an expression as complex as this? How do we do this operation? How do we do this? Not in the mind or in the mental state, but how really we have to do this in mathematics or in algebra. Here we are only talking about arithmetic, so let us see how this is done. We have to follow a process called PEMDAS. PEMDAS has different names, but I remember it this way, PEMDAS. PEMDAS is basically used in the US also as seen in schools. So when you have to evaluate this expression or simplify this expression, I have to say. So simplifying this expression, first we have to look at, see what is this? PEMDAS stands for PEMDAS actually. So P is parenthesis. So whatever comes inside a parenthesis, we have to first simplify. So we are doing 5 minus 2 equal to 3. That is the P. Then we have exponents. Are we having exponents in this expression? No. So we can ignore that. That's how it is. So then there is multiplication. Is there a multiplication in this? As of now, there is no multiplication in this. Then is there division? Yes, there is division. 18 divided by 6. See, for example, this is a division symbol. Most of us know. If we do not know, this is a dot hyphen dot. That is what is a division symbol. So therefore we do the 18 times 6 equal to 3. We did 5 minus 2 equal to 3 and 18 divided by 6 equal to 3. So this is the division part. We do from left to right. If there are multiple divisions, we will do left to right. If there are multiple multiplications, we will do left to right. If there are anything multiple, we will do left to right. First we will do the parenthesis, then we do the exponents, then we do the multiplication or division. It could be in any order actually. These two have the same priority. Multiplication and division have the same priority. Please read through the slides. Both of them have the same priority and we go from left to right. 4 times 3, how did this one come? So because we have this one next, multiplication. We did the division, we cannot do the addition now. So next is multiplication. So we do the 4 times 3. How did we get 4 times 3? 4 is here and 5 minus 2 was 3. That's how we get this 4 times 3, and we do the same thing again from left to right. Now finally what is left was, this was 3 and this whole thing became 3. 5 minus 2 was 3 and 4 times 3 is 12. Sorry, 12. So 18 divided by 6 was 3 and 4 times 5 minus 2. This is how you read it. 4 times 5 minus 2. We'll go into the details later. But for now, parenthesis. When we have a 4 like this in front of a parenthesis, it means it is multiplying this 5 minus 2. So 4 times 3 is 12. So that's how we got this 3 plus 12 equal to 14. That is the addition part. 3, 18 divided by 6 is 3. 4 times 5 minus 2 is 12. So that is how we got this 3 plus 12, which is 15, and the answer is 15. The reason I wanted to bring this up at this stage itself was the next section is going to look at these kind of problems for simplifying. So let us move ahead. Now you will understand why I talked about the order of expressions in the previous slide actually. So all of these examples will require you to understand and use the order of operations that is PEMDAS. For example, I'll just give you an idea. In this particular first expression, we'll have to do this first, 3 minus 2. Then we cannot do, we could do this also. We could do 3 minus 2 as well as we could do 10 times 1. Basically this whole thing will become 10 actually, if you really see. We could do this. Even in the previous example I could have done that. So 10 times 3 minus 2. The reason I didn't do that was I wanted to explain that there are no exponents. In none of these there are exponents. So you can ignore the exponents. So once you do the 3 minus 2, which is 1, then you can do the 10 times 1, which is 10. Then what we should do? Multiplication and division go together in the same priority and we can't do the addition. The only thing left is 30 divided by 5. So we should do this and get the answer 6. So this becomes 6 and this becomes 10, and 10 plus 10 is 16. That is what I have mentioned the answer here. I want you to try these exercises on your own. And we also talked about grouping. See the grouping part here. Within this parenthesis, there are two types of parentheses here. One square brackets and one the normal parenthesis. The first thing which will go in this grouping is the small parenthesis, whichever goes inside. If you would have used square brackets for this, then this will go first. Whichever is outer, that will go next actually. But normally the convention is we use the parenthesis for the inner brackets, then we will use the square brackets, and then if something else is there, we will also use the flower brackets. And that's how it goes actually. You can go any number of depth actually, there is no restriction on that. But as of now, so the first thing that you will do is evaluate 4 minus 2. Then you will do 3 times 2, which is 4 minus 2 is 2. So you will do 3 times 4 minus 2. And then you will do 6. 3 times 4 minus 3 times 2 is 6. So 6 minus 6 is 0. 3 times 0. This whole thing should become 0 in my opinion. So then you only have 5 and 23, which is what equals to 28. So please try to do these exercises. I'll leave it to you for them. I've given you the answers, but try to evaluate that and get a nice practice of these order of operations, PEMDAS. Next, let us see how we can evaluate an expression when the value of a variable is given to us. For example, here when we say x square, this is pronounced as x square actually, x to the power of 2, x square, and so on, and x raised to the power 2, but normally we will call this as x square in algebra. And here, just with this, we cannot do anything because we do not know the value of x. But we are given the value of x as 4. So what we can do is, we will be able to replace x with 4. X square becomes 4 square because we have replaced x with 4 actually. 4 square. 4 square is nothing but 4 times 4. 4 times 4 is what is 4 square, which is 16. So when we see an expression like this, 4 square, it means it is 16. We'll be seeing a lot of these things, but for now you should know that this kind of an expression, an exponent for a number, is those many times you have to multiply this number. The exponent is this 2, and this is the number actually 4. So you have to multiply 4 the exponent number of times, that is 2 times here. 4 times 4, which becomes 16. So x square in this case, given the value of 4 for x, becomes 16. Now let us take the second one, 3x, 3 raised to the power x. This is how you pronounce this, 3 raised to the power x. So x is 4 we know. So we make 3 raised to the power 4. We replace x with 4. So what does this mean? Like for example, we said here 4 raised to the power 2 means you have to multiply 4 by itself 2 times, 4 times 4. Same way here, we have to multiply 3 by itself 4 times. 3 times, 3 times, 3 times 3. That is what this means. 3 raised to the power 4. 3 raised to the power 4 is 3 times 3 times 3 times 3, which is 3 3s are 9 3s are 27, 3s are 81. That is how this is the notation for exponents. We are trying to learn what are exponents here, and that is what we are trying to see here. Now see this one, 2x square, this is how we read this. 2x square plus 3x plus 8. This is how you read this. Now we know the value of x is 4. So when you know the value of x is 4, when you see something like this, 2x, it means 2 times x. Anytime when you see a number and a variable without any symbol in between, it means it is 2 times 4. That's how you have to read it. 2 times 4. But now we know 4 is not just 4. 4 has an exponent 2. So it becomes 4 square. X becomes 4 and the exponent is already there. So it is 4 square plus 3 times 4. This is 3 times x. Just now we saw that 2x means 2 times x. 3x means 3 times x. So x is 4 we know, so we make it 3 times 4. Plus 8 stays as it is. It's a constant. See, this is a constant. So it remains as it is. Now we have to evaluate this. You have to use the PEMDAS. Now you have to start using the PEMDAS. So what does PEMDAS says? Parenthesis. Is there parenthesis in this? No. As of now, no. Is there exponents in this? Yes. That's why I have highlighted this here. Exponents are there. What is 4 square? We already saw. 4 square means 4 times 4. So 4 times 4 is 16 we know. So we replace that with 16 here. So it becomes 2 times 4 square becomes 2 times 16. Plus, now what is the next one? There are no more exponents in this. 2 times 16 plus 3 times 4 plus 8. We can't do any addition here because there are multiplications. There is a multiplication here. There is a multiplication here. So first we have to do left to right. 2 times 16 is 32. 3 times 4 is 12. 8 stays the same. Be very clear that we need to do some basic facts of multiplication like tables. 2 times 16, I can't look at calculator now. 2 times 16 is 32, we should know. So simple facts like that, if you know in your mind, you will be able to do things faster, which is very critical. Slowly you should get accustomed to that. So we got 32 plus 12 plus 8. That's how we get 52. 2x square plus 3x plus 8 given x equal to 4 will become 52. That's how you evaluate an expression when a value for a variable is given. Now there are some examples as exercises for you. Some of them, the first 3 of them I have worked for you, and here are the answers for them. And these I want you to simplify or evaluate based on your experience with what we have done earlier and also these examples. But I have given the answers for you. So for example, 6 square minus 4x minus 7 is equivalent to 185. I have given when x is equivalent to 3. That is what is the condition here. And here the condition is x equal to 6. In this case, x is 6. So what is this? 6 times 6 to the 6 raised to the power 3. So 6 6 are 36, 6 are 216. That's how it is. Take this one, 2 raised to the power 6. 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32, 32 2s are 64. That's how you get this. But I want you to work through step by step using PEMDAS if required. For example, here PEMDAS is required to do this. So you have to try all this and do it. Look for this. One example I will show you. This is x square and we are given x equal to 3. So x square becomes 3 square because x is 3. 3 square we already know that is nothing but 3 times 3 and equal to 9. So x square when given the value of x equal to 3 is nothing but 9. So please try these examples. These are very important. Please don't ignore any of these. Each example you should do. Even these do on your own and try to compare with these answers first. That's how you learn. Here I am trying to summarize the exponential notation actually. So for example, when you have 2 times 2 times 2 times 2, see writing like this, if you have to multiply 10 times like this, you will keep on writing 2's 10 times and you will not be even able to count properly. So that is the reason we have this kind of notation called the exponential notation, 2 raised to the power 4. That's how you read this. 2 raised to the power 4 is nothing but 2 multiplied by itself 4 times. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. That's how it becomes 2 times 4. Another important thing is in some texts you will see this notation. I also may be using this because in computers doing this is slightly time consuming and unnecessary. As long as we know this also means the same thing. This is 2 raised to the power 4. This is an exponent symbol actually when you write. So, but normally when you write with hand, you will always be doing this only. With pencil and paper, you don't do these kind of notations ever actually. This is how you will be representing it. So this is what is 2 times 4 is represented as this. The expression a raised to the power is read as a to the nth power. That's how you have to look at it. A to the nth power. 2 raised to the 4th power. That's how you read this. And for 2 and 3 exponent 2 and 3 alone, we have a special name because we commonly keep using this. A raised to the power 2 is normally read as a squared. We call it as a square. A squared, and this is a raised to the power 3 is normally called as a cubed. Beyond that, we don't have any specific names, or even if it is there, we rarely use them. We will only say a raised to the power 4, 2 raised to the power 4. But these two things have a special naming convention, a squared and a cubed. That is how we will be using this. And we will be seeing these a lot because most examples will be having this a square in the beginning, and later on we will get into a cubes once you get into advanced stages. So for now, just understand these exponential notation and we will go. We already saw what are terms actually in an earlier session or section. Here I am trying to formalize these things. So basically 7 is a term, y is a term, 5x raised to the power 2 is term. See how I am reading it. 5x raised to the power 2. Then 9a is a term and b5 is a term. Each one of these are called terms. When they are put together with a symbol in between, specifically an arithmetic symbol, it becomes an expression. And this is not Each one of them is an expression also in their own way, but normally we refer to them as terms when they are standalone like this. Then there is something called as coefficient, which is another important factor. Here I am only going to mention it. We will see later on in other sessions when we deal with them. When you see something like this, 3x, for example, 9a, 9 is a coefficient of a. That's how we have to see this. 3 is the coefficient of x. In 3x, the number in front of x is called as a coefficient. It actually means 3 times x. That is different story. Here I am only trying to bring out the fact that this number is called as a coefficient. There is no specific reason or anything. It has been named like that. So you have to know that there is something called as a coefficient, and that is the number that comes before a variable. We will deal with this in a lot as we go by. Another thing in this context we have to see is, many times we have seen, see for example, you are seeing y here. Y is a term we said. But this is actually 1y. That's how you have to look at it. X is actually 1x. If there is no coefficient, then the coefficient is 1. When no coefficient is specified, x becomes 1x. Even though it is never written. For your beginning days in your classes or in your lessons or in your exercises, examples and all that, you can always, I used to do this when I was starting to do algebra and all that. I used to write this as 1y. So I know that I have to add this 1. Many times we'll miss out this 1 when we are doing extended expressions, large expressions. When we have it, you will leave out this thing actually. So I normally used to write 1. So learn that x is actually 1x when no coefficient is specified. When I say no coefficient, this has no coefficient specified, but that doesn't mean that it has no coefficient. It has a coefficient of 1. That is one thing. Another thing is, and when x is specified like this, it has a coefficient of 1 as well as it has an exponent of 1. So when you say x square, you have x raised to the power 2 like this. But when you just say x, this is actually y raised to the power 1. It is 1 y raised to the power 1. 1 is not mentioned normally because it is meaningless actually to mention that. 1 is always there. 1 times x is still x only. So when no power is specified, it is x1. These two things you have to remember, because in big expressions, we will tend to forget these. Specifically, we tend to forget this one, 1x. We will not add this y, 1y. For example, it is 5y plus y. We will think 5y only. It is not 6y. It is actually 6y. 5y plus y is 6y. So when we say 5y plus y and something else more in that expression, some five more factors added and it's a big expression, in between there is a y, we'll ignore that. We'll forget that. So we have to be very careful that any term without an exponent, coefficient, that has a coefficient of 1 like this. That is important. Calling this beginning algebra session and not including anything worthwhile algebra, I thought is not good. So I am including one of the basic things that we need to understand as part of algebra. This part of the section is definitely algebra. We would not have seen this in arithmetic before this. So let us see what these are, what we need to understand. Like terms is an important term. That itself is a term you will be listening so many times as you go by in the next sessions and in algebra overall, in your school or in your college, anywhere. Like terms. Please note this down in your mind. Always mind. Note this down in your mind. These kind of things cannot be written down somewhere. Like terms. What are like terms? Slowly you will get to understand this. I'll be taking you through step by step, but for in this session and in this section specifically, we'll understand what are like terms. Like terms is a very, very important thing. Terms like 7 and 4 are like terms because 7 is a number, 4 is a number. Both are constants. So that is why they are called like terms. 7 and 3x are not. I'll come to this later. Let us see this. 5x and 3x are like terms. 5 and x, this is a term. X, 3 and x is a term. When variables are same and the coefficient can be anything, the variables attached to the coefficient are same, then they are called as like terms. And when the variables have exponents and the exponents and the variables are same, that is, when n raised to the power 2 and n raised to the power 2 here, forgetting about the exponents because, coefficients, because we need to know this one also has a coefficient of 1. That is not the case. That is not the context here. The context is this n raised to the power 2 which is attached to the coefficient. If these two are same, these are called like terms. N raised to the power 2, 5x, 3x, constants 7 and 4. In an expression, these can be added. That is what we are going to come to. For example, 7 and 4 are like terms, but 7 and 3x are not. Do you see that? 7 is a constant, 3 has a variable. X is a variable with a coefficient of 3. That's how you read this. X is a variable with a coefficient of 3, 3x. 5x and 3x are like terms because both of them have the same variable even though the coefficient is different. Whereas 5x and 5x raised to the power 2 are not, because x has an exponent of 1 and here x has the exponent of 2. So these are not like terms. Try to understand this. We'll see a lot of examples, don't worry about it. But here you have to clearly understand what are like terms. N raised to the power 2 is a like term, but n raised to the power 2 and n raised to the power 5 are not like terms. The variable has to be same, the exponent also has to be same if they are to be like terms, like this, n raised to the power 2 and n raised to the power 2. This is 1n raised to the power 2 and 9n raised to the power 2. So like terms are only concentrating on this part of the thing. It is not concentrating on the coefficient. Same here, like same variable x and x. X here, those become like terms. So here I don't like these English explanations. We have to understand by working with examples, and we will see those as we go by, and some in today's session itself. Terms are either constants or have the same variables or have same variables raised to the same powers are called like terms. See, terms that are either constants, 7 and 4, are like terms, or have the same variables are like terms, or have the same variables and raised to the same powers are like terms. Are you able to see this? This is very important factor, and we will have to know this to do a lot of operations in algebra. Now let us see how to simplify an expression which has like terms. See this, 4x plus 7x plus x. This is actually 4x plus 7x plus 1x, as I was referring to in the previous section. Now all of these are having three terms, the same term. X is the variable here. All of them have x raised to the power 1, whatever the coefficient is. X raised to the power 1, x raised to the power 1, x raised to the power 1 with coefficients of 4, 7 and 1. So in this kind of a situation, when the variable is same, this is 1 x raised to the power 1, 7 x raised to the power 1, 4 x raised to the power 1. So I was also mentioning about this, adding this 1. I put it in red because that will give you the idea that you have to add this guy also with 1. Otherwise, if this 1 was not there, we may think that I had to add only 4 and 7 in a complex expression. So what we can do in this case to simplify this expression 4x plus 7x plus 1x is we can add up these. First algebra you are learning here. 4x plus 7x plus 1x can be added. All these coefficients can be added. 4 plus 7 plus 1. So when you add 4 plus 7 plus 1, because all of them have the same variable with the same exponent, even though the coefficients are different, we can add them together like this. 4 plus 7 plus 1 equal to 12, which makes it 12x. 4 apples, 7 apples, 1 apple. What is the total when you add them? It becomes 12 apples. That's how you have to look at it. Like terms. Apples are apples. Apples and oranges are not same. This is the most important thing for now you have to understand. As you go through hundreds of examples later on, you will get comfortable with this. But at this time, adding these with same variables is what is called as like terms. So when there are like terms, you can add, subtract, multiply, whatever you have to do, you can do. But in this case, we are only starting with addition. So we add the coefficients and then say 12x. So if you get an expression like this and you are asked to simplify this, you will just add those coefficients and say 12x. I am sure you are understanding this. You can comment on in the comment section if you need any help. I will be always able to answer. Let us see a slightly complex example. See this. 2x raised to the power 2 plus 3x plus 7 plus x raised to the power 2 plus 4x plus 5. That is the expression we have to simplify. We have to follow all the PEMDAS operations, but here there is no much of PEMDAS involved, but we will have to still see what we can do first. So we will see. How do we simplify this? Always remember there is a 1 in front of this x. Yeah, that's all. That is the only one which is not having anything, no coefficient. This one has a coefficient, this one has a coefficient, this one has a coefficient, everything is there. So what we need to see is what are like terms in this. That is what we have to do. We have to simplify this kind of an expression. I have color coded this for you so that you easily understand. Let us see the simpler ones first. See, 7 is a constant, 5 is a constant. So basically we can add these two. Everything is addition in this. As of now, we are not confusing ourselves with multiple arithmetic operations. Everything is addition. So we can go from left to right actually. So 7 and 5 can be added. 3x and 4x can be added because both of them have a variable with an exponent of 1. 3x raised to the power 1 and 4x raised to the power 1. Then we have 2x raised to the power 2 and x raised to the power 2, which is nothing but 1x raised to the power 2. So we are not worried about coefficients when we talk about like terms. We are only worrying about this part apart from the coefficient, x raised to the power 2. So these two are also like terms. So we can now start adding. So let us do that. 2x raised to the power 2 plus 1x raised to the power 2 becomes 3x raised to the power 2 because we are adding 2 and 1 here in front of this x. 1 will not be written. Please remember, 1 will never be written. I am only giving you an idea that if you write down, it will be easy for you for now, not at a later stage. You will never write 1. Then go to the next step, 3x plus 4x. That becomes 7x. 3 plus 4 is 7 and x remains the same, 7x. 3 apples plus 4 apples becomes 7 apples. 2 apples plus 1 apple becomes 3 apples. Then constants are added just like that. 7 plus 5 is 12. So the simplification of this expression is this. 2x raised to the power 2 plus 3x plus 7 plus x raised to the power 2 plus 4x plus 5. See how I am reading that also is simplified as 3x raised to the power 2 plus 7x plus 12. This cannot be further simplified. You learn all these things later. There is nothing to simplify there because I cannot add 3x raised to the power 2 with 7x, or I cannot add 7x to 12 because this has a variable and this does not have a variable. This is a constant. This is a variable with a coefficient. This is a variable with a coefficient and an exponent. So none of these are like terms anymore. So we cannot do anything. This is called as the most simplified form of this expression. You will get in your tests, in your classes, these kind of questions. Now try to answer these. This is your exercise for today. Try it. If you are unable to do, you can always let me know. But I have given you the answers here. But you should go through the steps, step by step. Try to go what are the like terms in this. It's almost similar to this example that I have shown here. So you should be able to do, and we can go forward with that. There are a lot of things that we'll be learning going forward. So try out these exercises. I know we dealt with a lot of concepts in this particular session because these are assumed that we know except the last concept that we learned, which is like terms. So it is very important session for you to go to the next step of algebra. I may cover more, but I'll come to the more part after covering some algebra actually, so that we are all interested in doing algebra rather than just learning the fundamental concepts or the prerequisites. Learning algebra requires you to understand all these concepts actually and do a lot of practice. Practice is the most important thing. And one last thing I want to say is always use square ruled paper, because when we come to graphing and things like that, it is very critical to do. And use a pencil so that you can easily erase, change, do whatever modifications you want, and you will be able to work better. Today everybody uses iPad and things like that, but my suggestion is always use a square ruled paper with pencil with an eraser, and that is the best way to learn mathematics, and specifically algebra, where you will be keeping on erasing multiple times when you go forward. And if you really like this session, please like, share and subscribe, so I will be able to spend more time and it will encourage me to make more sessions for all of you. Thank you so much for staying so long with me. Good luck with your algebra.